The problems dealing with strong induction, and the problem is as follows. I need to show that whenever n is greater or equal to 3, f subscript n, and this over here is the nth Fibonacci. So we're going to define this as the nth Fibonacci 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 number. Okay, so f of n is greater than alpha to the power of n minus 2, where alpha over here happens to be some constant, which is equal to 1 plus root 5 over 2. Okay, so first thing, because we're using strong induction, I'm going to define my proposition. So the proposition P of n is the statement. Is the statement that f of n, the nth Fibonacci number, is greater than alpha to the power of n minus 2 when n is greater or equal to 3. Here's the entire proposition of my problem. Now what I'm going to do is I'm going to define my bases. So the bases over here, I'm going to use a slightly different color. Let's use yellow for this. So I'm going to say P of 3. Okay, and I'm using 3 here because I know that the constraint here is I'm only looking at those numbers that happen to be greater or equal to 3, and 3 happens to be one of the smallest number in this universe of numbers that I'm currently looking at. So P of 3 in this case is when n equals to 3, this becomes f of this becomes f, the third Fibonacci number, is greater than alpha to the power of 3 minus 2. And the third Fibonacci numbers, if I just give my Fibonacci numbers over here, it starts from 0, 1, and 0 plus 1 is 1, 1 plus 1 is 2. And again, this is pretty just straightforward definition where I'm saying the f of 0 is 0, f of 1 is 1, and the nth Fibonacci number is f of n minus 1 plus f of n minus 2 for all n that happen to be greater or equal to 2. Okay, so here's the definition. Here's the definition of Fibonacci numbers that I'm using, and by using this definition, I can see that the third Fibonacci number, which is f of 3, is equal to, so this is f of 3 is equal to f of 2 plus f of 1. F of 2 happens to be this is 1, and f of 1 in this case happens to be 1. 1 plus 1 gives you 2. So f of 3 is basically 2. Is greater than alpha to the power of 3 minus 2, which is 1. Alpha happens to be a constant, which is 1 plus root 5, 1 plus root 5 over 2. And this entire number over here, if you plug it in a calculator, is approximately 1.60. And I can see that 2 is greater than 1.60, so my basis over here for at least P of 3 is true. Now what I'm going to do is I'm still going to solve this for P of 4. Okay, so for P of 4, which is f of 4 is greater than alpha to the power of 4 minus 2, which is f of 4 is greater than alpha of 4 minus 2, that's 2. Again, you know alpha is a constant. You can get the fourth Fibonacci number by using the sequence here. Okay, so that gives you 2 plus 1 is 3. This is f of 0, f of 1, f of 2, f of 3, and f of 4 there. Okay, plug in the calculator and you can see that this inequality is also true for P of 4. All right, now what we're going to do is we're going to solve this, we're going to state an inductive hypothesis. So my inductive hypothesis in this case is, I'm just going to create some space here. So the inductive hypothesis here is that, again, I believe I'm using strong induction for this problem. So what I do know is that P of 3 and P of 4, and this is true for all of these j's that go up to P of k. So I choose some arbitrary k out here, and these j's that happen to be between 3 and k. For all j's that I'm looking at that happens to be between 3 and k, I know that the statement P of j is true for all these j's over here. What does that mean? Well, that means that given this entire hypothesis of my argument, I'm going to now show that P of k plus 1 is also true. Okay, so that's the inductive hypothesis. And what I want to show you is P of k plus 1 is also true, which means that I would now like to show P of k plus 1, which is the statement, that if I go into my expression P of n and I replace n with k plus 1, k plus 1 is greater than alpha power of k plus 1 minus 2, which is P of k plus 1 is f of k plus 1 is greater than alpha to the power of k minus 1. Okay, this is something that I would like to show you. Something that I would like to show you is true by using my inductive hypothesis here in yellow. Okay, so let's show that. So what I'll do is, let me create some space here again, and I'm going to use a different color. Let's use blue. And what I'll show now is, because I know that for all j's between 3 and k, for some arbitrary k out there, all of these proposition P of j is true, I know that the following inequality, f of j is greater than alpha to the power of j minus 2 is true. Okay, so I just looked at my proposition, replaced the n with a j, and I'm making sure my j is between 3 and k, so I know this is actually true here. Now, instead of using j here, let's just make sure this is k. Let's just make that change here. Let's make it f of k. Okay, I'm just making sure I'm looking at the very last item here, so let's make it k minus 2. Okay. Now, because I know that this inequality over here is true, and also if I take this inequality and if I add to this inequality f of j minus 1, so let's say f of j minus 1, I add f of j minus 1 to the left hand side, so that makes it I'm just adding j minus 1 to the left hand side of this expression over here in the box. So given this inequality in the box over here, I'm adding f of j minus 1 on the left hand side and adding f of j minus 1 on the right hand side. Now because this j over here varies between 3 and k, and also I'm making sure that j minus 1 over here is some j minus 1 Fibonacci that also happens to be between these ranges over here, between 3 and k, I can now do this as follows. I can just say f of j minus 1, which is this piece over here, plus f of k is also greater than, I can replace f of j minus 1, with the statement that this is alpha to the power of j minus 1 minus 2 plus alpha power of k minus 2, and which becomes f of j minus 1 plus f of k alpha. This becomes j minus 1 minus 2 gives you minus 3 plus alpha to the power of k minus 2. Okay, now what I really want to make sure is that my subscript j minus 1 over here is a number that actually satisfies this inequality, where it actually varies between 3 and k. I want to make sure it doesn't exceed these bounds, because within these bounds I do know that the statement P of j is true. What is one such number that happens to be true between 3 and k? Well, one such number that happens to be true between 3 and k is the number k minus 1. So instead of saying j minus 1, what I'll do now is I'll just say this. All right, let's look at k minus 1 plus f of k is greater than alpha to the power of k minus 3 plus alpha to the power of k minus 2. Okay, so I just made sure that within these bounds over here, which is, if I look at this number line, here is 3, here is k, and any number between 3 and k, this inequality of P of j is true. So I happen to choose this j that happens to be right here, which is k minus 1. Okay, and this is again strong induction, because I do know in strong induction that a statement P of k, which is this piece over here, P of k, and the statement over here P of k minus 1, both are actually true. And because both are true, I have replaced the on the right hand side where I actually had f of g minus 1 with a number that happens to be smaller than this, which is alpha to the power of k minus 3. Okay, now given this entire expression over here, I can still make some changes. So starting from this pink box here, what I'll do now is I'm just going to maybe erase some pieces over here. Now, remember, alpha is a constant. Okay, alpha is a constant, and because alpha is a constant, what that means is this alpha square is equal to, just by definition, let's do it this way. Instead of saying alpha square, what I do know is alpha to the power of k minus 1, just by definition, is equal to alpha square times alpha to the power of k minus 3. Okay, so just with the exponents here, and if I see k minus 3 plus 2 gives you k minus 1, so this is just by definition alpha to the power of k minus 1 is equal to alpha square times alpha to the power of k minus 3. Now what I also know is that in this quadratic equation of f of x equals to x squared minus x minus 1, if I look at this quadratic equation, and in this quadratic equation, if I substitute x for alpha, this is going to give you alpha squared minus alpha minus 1, and this alpha squared minus alpha minus 1, this is what alpha is. Take that alpha, plug it into this expression, and what that will give you is basically f of alpha is equal to 0, which means alpha squared minus alpha minus 1 is equal to 0, which tells you that alpha squared is equal to alpha plus 1. Okay, so what I do know is that alpha squared equals alpha plus 1, which means that if I were to start with this expression that I had earlier, I can now say alpha to the power of k minus 1 is equal to alpha squared. Alpha squared is equal to alpha plus 1. So I'm going to put alpha plus 1 there, times alpha to the power of k minus 3. So alpha to the power of k minus 1 is equal to, if you do a little bit of arithmetic over there, this is equal to alpha to the power of k minus 2 plus alpha to the power of k minus 3. Okay, so coming back to the spring box then, f subscript k minus 1 plus f of k is greater than alpha to the power of k minus 3 plus alpha to the power of k minus 2. I can take everything on the right hand side over here, which is alpha to the power of k minus 3 plus alpha to the power of k minus 2, and replace that with alpha to the power of k minus 1, which means that this expression now becomes f of k minus 1 plus f of k is greater than alpha to the power of k minus 1. Okay, and this is exactly what I want to show you in my p of k plus 1. So remember, f of k minus 1 plus f of k. If I take the kth Fibonacci number and add it to the previous k minus 1 Fibonacci number, what that means is I'm going to get the k plus 1 Fibonacci number. Okay, so left hand side becomes f of k plus 1, which is greater than alpha to the power of k minus 1. And this is the expression that I wanted to show you.